guess the topic for this chapter? Right, waves. Well, what exactly is a wave? Well, in some sense, we know a wave when we see one. It is some disturbance in water, something bobbing up and down. Actually, a wave is a mean by which energy can travel through a medium being either a gas, a liquid, or a solid. We will also see in this set of lessons that energy can also travel in a vacuum, in the absence of a medium. And that special kind of way for energy to travel is called electromagnetic radiation. Electromagnetic radiation is light. And we'll see that electromagnetic radiation is produced whenever an electrically charged particle or object is accelerated. But first, let's go through some basics about waves. As we said, a wave is a traveling disturbance that carries energy from one place to another without matter moving from that one place to another. There are different types of waves, but in this set of lessons, we'll focus mainly on two types. One would be compression waves, or sound waves, and the other will be electromagnetic radiation, which includes light. You see at the bottom of this slide a set of wavy patterns, and as we go on, we'll see what all of this means. And we'll also gain an understanding of the color coding, the red going to blue and violet. So let's talk about the properties of waves, and we'll go a little bit into physics here. A wave is a sinusoidal waveform. Sinusoidal is a big word. It's got a lot of vowels in it. But basically, it means something goes up and down in a wave. A waveform can be described by a number of characteristics shown in this slide. One characteristic is what we call the wavelength. If you look at the bottom of this slide, you see an example of a sinusoidal waveform that goes up, then it goes down to a trough, then it goes up through a peak and down through another trough. A wavelength, this first characteristic, is defined as the distance from peak to peak, or the distance from trough to trough, whichever way you like to look at it. The wavelength is measured in units of distance, and in science we generally measure units of distance in meters or centimeters, the metric system, and we usually give it a symbol lambda, the Greek letter lambda. A second characteristic is the frequency of the waveform. The frequency is the number of these up and down, number of these complete waveforms, or the number of crests per second. So the number of times a waveform goes up and down per second is the frequency. You can have high frequencies, or you can have low frequencies where it takes a long time to go from peak to peak. Frequencies are measured in reciprocal seconds, seconds to the -1, or what is called hertz. A hertz being a reciprocal second, that is the same thing. And hertz is named after Heinrich Hertz, a German physicist who was a leader in the understanding of electromagnetic radiation. A period is a time in second from one crest to the next. Now, in this plot, I'm showing distance on the x-axis. One could also have time on this x-axis. So if this were time, the time from one peak to the next would be the period. Essentially, a period is the reciprocal of frequency. I know this is getting a little bit into math. The next one, however, is easier to understand, and that's the amplitude. The amplitude is essentially the height from the midpoint, the height of the crest. This will be related to the loudness, if we're talking about sound, or the intensity of light, if we're talking about light. Yet another property of waves is the velocity of the wave, the linear speed or the linear velocity at which the wave propagates. Sound, for example, travels at about 340 meters per second in air. Light travels 1,000,000 times faster. Light travels 3 times 10 to the 8th meters per second. In our everyday experience, we think sound travels pretty rapidly, but actually not so fast. It takes sound about 5 seconds to travel 1 mile. So if one Saturday afternoon I'm out in the backyard and I hear a roar go up in the direction of campus, I know that our team has scored a touchdown 10 to 15 seconds earlier. Think about that. It takes 5 seconds to travel a mile. Just as an interesting calculation, if a sound signal could travel all the way around the world without dispersing, it would take, believe it or not, 32 hours. Long time. So we think sound travels rapidly, but actually it's much slower compared to how fast light travels. Light travels approximately 1 million times more rapidly than does sound. For light to actually travel around the Earth takes a little over 1/10 of a second. Before leaving this slide, let me point out an important equation. The velocity, the linear velocity, v, is equal to the product of the wavelength of a wave times its frequency for a given type of wave. For a sound wave having a velocity of 340 meters per second, that velocity is equal to the product of the wavelength of that sound wave times its frequency. Likewise, for light, which moves with a linear velocity of 3 times 10 to the 8th meters per second, that velocity, the speed of light, is equal to the product of the wavelength of light times the frequency of light. We'll see applications of that in one of our next lessons. In this next slide, we show that waves travel through media in 2 basic ways. The first is called a longitudinal or compression wave, and the second is called a transverse wave. Now, to illustrate both of these, imagine taking a slinky. Now, this must be a very relaxed slinky, one you've probably been playing with every Christmas since you were 4 years old. But if you have this very relaxed slinky and you affixed one end to a wall, and at the other end you give it a push, there would be this area of compression and then relaxation or dilation, compression, dilation, compression, dilation. And the energy from your initial push on one end of the slinky would be felt at the other end after some period of time. So this would be a longitudinal or compression wave. It turns out that sound moving through air is a longitudinal or a compression wave. Now, the second way energy travels as a wave through media is a transverse wave. And in this example, imagine having the slinky, or a very relaxed slinky again, or maybe a jump rope, in which we input energy to the slinky or rope by shaking it up and down, and you would have a sinusoidal wave that is created where the energy would reach the other end, the wall. Waves on the surface of water travel as transverse waves. So there are 2 basic ways in which energy travels as a wave through media: longitudinal or compression waves, or transverse up and down waves. This slide illustrates the waveforms again and focuses on how there can be long wavelength, low frequency waves, such as the one on the top. Notice how long the wavelength is in this case. Or we can have short wavelength, high frequency waves, as shown in the bottom. As I said earlier, the bottom axis can be represented as either distance or time, and that's because for a particular type of wave that has a constant velocity, distance and time are proportional to one another. Don't worry about that. But just notice that you can have either a long wavelength, as measured in our distance units of meters or centimeters, or you could have a short wavelength. And if this axis is time, it could take a longer time for a waveform, that would be a low frequency, or it could take a shorter time for a complete waveform, that would be a high frequency. So high frequency would be the very choppy ones, and low frequency would be the slow, long, drawn out waves. Okay, we're going to pause, have a brief quiz, and then we'll go on to the next video lesson in this set, in which we will talk about how waves can also travel through solids, and that there are significant consequences to that. Earthquakes. See you in a while.